So, welcome back to this session. It's my pleasure to introduce the speaker, Professor Arvind. Arvind is on the faculty in this institute, IMSC. He is a member of the theoretical computer science group, but he has a strong background in mathematics. And as you can see from this title, there's algorithmic questions in finite group theory. So groups are mathematical objects, and many of you have studied them from a purely mathematical perspective. Algorithmic questions suggests a computer sciencey perspective, and of course there's computer science coming into it, but although the problems are posed that way, the approaches to solve them, the solutions do involve a lot of non-trivial mathematics as well. And Arvind is going to tell us more about this.
Thank you. So thank you for giving me a chance to talk in this nice workshop. Always nice to talk to a large audience of students. Please feel free to interrupt me. Let's treat it like a kind of interactive thing so that I know exactly how to pace myself as I go along. So here is a quick plan of the talk. To begin with, some simple background on permutation groups and basic algorithms. And then this is somehow the heart of the talk, computing fixed point free elements of a permutation group. I'll explain what it means as we go along, both existence and computation. Okay. And then if time permits, two other algorithmic topics, computing small bases for permutation groups, and then maybe even random subproducts in groups, which is a very useful tool in doing efficient computation in groups. Okay. But most probably I'll just be able to do the first two things. Let's see how it goes. What is in this talk for you? Okay. Not much in terms of the group theory content. I'll disappoint the specialist group theorist or algebraist because everything is from a first course in algebra. For an algorithmist also, it's pretty basic. Okay, simple algorithmic ideas, nothing fancy at all. Probably what is new is the cocktail of groups and algorithms together. And I'll try and make it a heady cocktail for you. And I'll be very happy if it motivates teachers and students to experiment with similar cocktails in other math courses like, say, linear algebra or anything else for that matter. If you can look at the material through an algorithmic lens and look at common day-to-day math objects, maybe they'll show new facets through an algorithmic lens. That's what I want to convince you about. Okay. So let's get started. So begin at the beginning. Sn is the group of all permutations on n elements. You know what permutations are, simply bijections from 1 to n to itself. And you know how to compose permutations. They form a group. Identity is the identity permutation and so on. You know how to invert permutations. And you know that this group has many elements in it. N factorial is large for me, even when n is only moderately large. And a permutation group for me is any subgroup of Sn. Okay, that's what I call a permutation group. Of course, we know from Cayley's theorem that every finite group is a permutation group sitting inside some Sn, but that some Sn may have a very huge n, and for me n is small. So since these numbers matter for me, when I say Sn, I mean n is a comfortably small number for me, like 100 or 1000, and not 2 to the power 100 or 100 factorial, okay, which is more than the number of fundamental particles in the universe. So I want to deal with reasonable numbers. N is a reasonable number, and anything that sits inside Sn is what I call a permutation group. So Cayley's theorem is not very relevant in this context. Okay. How do I describe a permutation group? Again, I don't want to list down all the elements because n factorial is huge for me. And the right way to describe a permutation group is to give a generating set for it. Because that way I can describe any subgroup of Sn through a small set of generators. Okay? So what do I mean by the permutation group generated by the subset S of permutations? It's simply the smallest subgroup of Sn which contains the subset S. Equivalently, every element of that subgroup can be expressed as a product of elements from the subset S. In that sense, it spans that subgroup in the vector space sense. Except that here you may have long products, not linear combinations. So, but still every element of this subgroup can be expressed as a product of elements of S. So, these are generators for that subgroup. Okay. So, let's get on with things. Why did I say that every subgroup has a small generating set? That's because every finite group G has a generating set of size log cardinality G to the base 2. And here is a simple argument for it. Start with any element different from identity, call it G1. If the group generated by G1 is not the whole group, if G is not cyclic, then you will need another element G2. So let's throw that in. I have the group generated by G1, G2. If that's not enough, I'll throw in G3 as well. It's not enough because there is something that's not covered by the current subgroup that I have. And when I throw in a new element, by Lagrange's theorem, I know that the size of the group must at least double because the size of subgroup divides the size of the group inside which it sits. So at every stage, I at least double the size of the group that I generate, which means by the time I pick log cardinality G to the base too many elements, I have a generating set. So in particular, when we are talking about subgroups of Sn, log of n factorial is enough for me to describe any subgroup of Sn by generating set. And that's good for me because then I know that to describe one permutation, I need a list of n, an ordering of 1 to n basically, an n tuple, an ordering of 1 to n. And if I have n order n log n factorial is at most n log n. So if I have that many elements, well, it's the entire description is of size n square log n small numbers ranging between 1 to n. And that's small for me. Okay, so I hope you're comfortable with this, my intuitive idea of small and large. N is small, n square is small. And theoretically, even n to the 10 is small for me. Any polynomial in n is small for me. 2 to the n is large, n factorial is large. Okay. So giving a generating set for G is a succinct way of describing a finite group G. And when I want to do algorithms on finite groups, I could take a group as a big multiplication table as well, but if I want to deal with larger groups and yet manage with presenting it with just a generator set as input, I'll be happy. And that's what I want to do with permutation groups. Here are some more definitions and notation. You take any point I in 1 to n, the image under pi is, I write it as I to the pi. This is a better notation than pi applied to I because then I can compose permutations from left to right rather than right to left. Notation invented by Wieland, I believe. A point I in 1 to n is a fixed point if pi doesn't move I. And let's denote the number of points fixed by pi as fix of pi. The next important object in permutation groups is orbits. Okay. So G is acting on the domain 1 to n, and if you take a point I, it moves that point to different places when you apply different elements of G to it. So you say I and J are in the same orbit when there is some element of the group which maps I to J. Okay? And the orbit of a point is the set of all points to which it can be moved by the group acting on it. Okay? So clearly it's an equivalence relation, two elements being in the same orbit, and it partitions 1 to n into orbits. Okay? So clearly they are fundamental as well. And a group is called transitive if any point can be moved to any other point by the group. For example, the single cycle 1 maps to 2 maps to etc. up to n, which maps back to 1 is a transitive group. Okay. So the group is transitive if there is exactly one orbit. And now let's discuss some algorithmics, things that I already told you about. How do I represent a permutation? Just as the n tuple of the image is a 1 to n. Okay. So it's some reordering of 1 to n. Or if I want random access, I can also think of it as an array indexed by 1 to n. Sometimes that's useful when you're writing programs. And I will think of applying a permutation to a point as one step, one operation. And therefore, if I want to compose two permutations, I do a left to right composition as I told you. I have to do pi applied to I and then psi applied to the result. So two operations, that's also, well, I have to do it n times because I have to do it for all the points to figure out what the entire permutation is. So it costs n. So these are the basic operations, and everything that I'm going to count is in terms of these operations. How much time does it take? I know roughly it takes n unit cost operations to multiply two permutations. That's all I need to know. Rest of it is simple calculations. So when I want to figure out how efficient is an algorithm that I've designed, it's enough for me to essentially count how many permutation compositions I've done. If I want, I'll also look into how many times I've applied pi to different points. But that's about it. Okay, so this is clear because I just told you elements are n tuples and subgroups don't require generating sets of size more than n log n. So something like n square log n is enough, although you might give a subgroup with a larger generating set. Okay, so now let me just define the terms, the rules of the game. Efficient means polynomial in n many operations. That's what is efficient algorithms for me. And exponential in n is inefficient for me. And you understand why. So let's discuss a simple example, a warm-up. I'm given G by a subgroup G of Sn by a generating set, and I want to compute the orbit of a single point. How do I do it? I will simply apply all the generators to the point I. It will give me a set of points. I'll again apply all the generators to these points. If the set grows, I'll have to try again. If at any point of time I get a set of points which doesn't change when I apply the generators to that set of points, clearly I can't reach out any further from that orbit. So that's the orbit, and that's what this little program does. Just to remind ourselves that it's also computer science, I've written a little program there. Input is a bunch of generators for G. I initialize the orbit as I, and then as long as the orbit changes, I apply all the generators. Oh, what I've written is not nice. This I should have been in O. I apply all the generators to, this S should have been O, sorry. That's a typo. But you understand how it works. And so this while loop here, it's going to run for at most n steps because there are only n points in the entire domain, 1 to n. And every time either I grow, if I don't grow, I'm going to exit. And if you count carefully, the number of operations we are doing is order n times k, because I'm doing this to everybody in O and there are k many generators. And since the loop is n, I'm doing n square into k operations and all. So this is the only time I'm going to tell you, count the number of operations in detail. After that, I will hand wave. Okay. So here is a basic algorithmic problem that I want to solve. And this is what I'm going to use later to algorithmize Jordan's theorem on fixed point free elements. in permutation groups. So given as input a permutation pi in Sn and a subgroup of Sn given by a bunch of generators, I want to test if pi belongs to G, and if so, I want to express pi in terms of the generators. Is it a reasonable question to ask? I want an efficient algorithm for this. Asking, if I simply want to give a yes/no answer, is pi a member of the group G? That's the reasonable question to ask, because I only want a single bit as the answer, yes or no, single bit of information. But how do I express pi in terms of generators? If I simply want to write pi as a product of generators, as a list, gi1 into gi2 and so on, that could be a huge product. For example, even in this trivial case, suppose G is a cyclic group generated by this carefully chosen permutation G, where G is a product of disjoint cycles of different prime lengths. I know that the order of a permutation, what is the order of a permutation? Which is, say, product of cycles of length n1, n2, nl. What is the order of a single cycle? It's the length of the cycle. If I give you a bunch of disjoint cycles, what is the order of that product? It's the LCM. And that's why I've chosen different primes here, to make the LCM as large as possible. And by the prime number theorem, you can easily check that the order can become as large as 2 to the power square root n log n. Okay. So that clearly, if I want to express an element of G as in terms of the generator, I shouldn't write it as G into G into G, because that is going to be exponential in square root n log n. And worse things can happen, of which I don't have a ready example. When S is G1, G2, Gk, it's some non-commutative, non-abelian group with a bunch of generators, it could require huge expressions. So clearly it's not the right way to express an element of the group as a list like this. In the case of a cyclic group, I can obviously do some clever things. How would I express G as, how would I express any element of the cyclic group using a generator? I would write the exponent as in binary, and then I know that I can get to different G to the power 2 to the power i's by repeated squaring, and then pick all the correct set of G to the power 2 to the power i's and multiply them, right? That's what will give me G to the power any element. I need to do something similar for arbitrary subgroups of Sn. Okay, so we need to have a more compact way of representing pi in terms of its generators. So this is what I just now told you. And this little program which does this repeated squaring of G, collects all possible relevant G to the power 2 to the power i's, and picks out the good ones, namely the ones for which Bi is 1. This is called a straight line program, computing G to the power G. A straight line program is a program where there are no loops. Although I've written this with 2 loops, you should unwind these loops and it will become a long straight line program. It's a compact way of writing that. But there are no branching statements, there are no loops. So let me formally define a straight line program. So suppose G is a subgroup of Sn generated by G1 to Gk, and pi is an element of this group G. A straight line program for pi would be something like the following. The first k lines will have assignment statements of the form xi is assigned gi. And then each subsequent line will be xi is assigned xj times xk, where xj and xk are already computed from the earlier lines. Like we did the repeated squaring and then multiplied the pre-computed g to the power 2 to the power i's, something more general than that. A simple idea of short expressions, how to get short expressions for elements of g in terms of the generators. Okay. And here is a nice fact which we are going to see in the course of the algorithm that I'm going to describe, that any element of, so suppose G1 to Gk generates some subgroup of Sn, any element of the subgroup can be written as, can be expressed as a straight line program of length at most polynomial in n and k. So it's going to be a short straight line program, not an exponentially long straight line program. Okay, remember that we started off with a membership problem. I want to design an efficient algorithm to test whether pi belongs to the group generated by S, and if so, express pi in terms of the generators through a straight line program. So to that end, I need this notion of strong generating sets. A very simple idea. So let G sub I denote the subgroup of G which pointwise stabilizes 1 to I. Do you all understand what pointwise stabilizer means? So every element of G sub square bracket I is going to map 1 to 1, 2 to 2, etc., I to I. And I am interested in this pointwise tower of stabilizer subgroups. Starting with G, I fix the point 1 and then I fix the point 2, and when I fix n minus 1 points, I get the identity. And my strong generating set is simply going to be coset representatives of G, of G1 and G, G2 and G1, and so on. I want to collect all these coset representatives, find all these coset representatives and take the union, and that's what I call a strong generating set. So in what sense is it strong? It's because every element of G can be expressed uniquely as a product of some one coset representative here multiplied by one coset representative here all the way down. I'll simply have to pick the right coset in which the right coset of G1 and G in which the element pi sits, and take that coset representative and then descend the tower in the same way. Take the right subcoset of that coset that I picked in which the given element pi sits, and so on. That will give me a bunch of coset representatives, one from each layer, and that product will actually be a unique way of expressing pi. It's obvious. So if I can compute a strong generating set from an arbitrary generating set, then I can do many things in one shot. I can compute the order of the group G. What is the order of the group G? I simply need to count how many coset representatives I have here. So product of cardinality Ti clearly is the order of the group G. By Lagrange's theorem, we know that. I can compute the order of the group G. I can also find out, once I have a strong generating set, how to express a given element pi in terms of the elements of the strong generating set. All I need to do is look at all the coset representatives and see which is the unique one which does the same thing to the point 1 as pi. If none of them do the same thing as pi does to the point 1, pi is not in the group G. Otherwise, that is the coset representative I should pick as pi 1. And then I continue. I will multiply pi. So I'll consider pi times pi inverse, which will belong to G1, and I'll repeat the same process. I'll find all the unique coset representatives simply by seeing which of the coset representatives my current element agrees with in its, when I apply it, say, in a general level to the point I at the ith layer there. And that's something that I can easily do. strong. Short is simply this n is short for me because 2 to the square root of n log n is long for me. Because n is a small number like 100 or 1000 and not 2 to the power 100, I call it short.
When G is Sn, could you give an example of a strong generating set?
Yeah, you can trivially fill up transpositions. I mean, you can use.
What would the size
be? You'll fill up the entire table. You will end up filling up the entire table.
No, what would be the size of Ti for it?
It will shrink, no? So when you look at the ith layer, there will be at most n minus I elements because I would have fixed 1 to I. I will only need to know I can map I plus 1 to I plus 2. I'll put a transposition for that. I plus 1 to I plus 3. I'll put a transposition for that. So I'll get n minus I transpositions in the ith layer. So I'll get n factorial like that. Good. Yeah. So yeah, that's right. That's a good point. At the ith layer, you can have at most n minus I coset representatives because you would have fixed 1 to I. So there are at most n minus I places to which I can be mapped. I plus 1 can be mapped, sorry. So, yeah, I have hardly any examples in the course of my lecture. Feel free to stop me whenever.
So that's big, right? The set is big then.
Yeah, the size of my new generating set is n square at most. Because that's a good question again. What is the size of cardinality Ti? At the first layer, it's at most n, n minus 1, and so on. N plus n minus 1 plus n minus 2. So that's at most n square. So a strong generating set is of size at most n square. N is small, n square is small, 2 power n is big, n factorial is big. So this is what I just told you. Once I have a strong generating set, membership testing was very easy for me because pi is in G if and only if pi is in G1 of pi 1 for some pi 1 which is the first transversal, one of the cosets. So pi does the same thing as pi 1 to the point 1. And then I take pi into pi 1 inverse and recursively do the same thing with G sub 1 and so on. So therefore the question boils down to how do I find a strong generating set for G when it's given by an arbitrary generating set? Okay, so the first thing is to find, so I want to find all the transversals, T1, T2, the coset representatives for each layer in my tower of pointwise stabilizer subgroups. Finding T1 is easy because we know how to compute the orbit of 1. And when I compute the orbit of 1, one thing I forgot to tell you is that we can keep track of which group element maps 1 to the different points in the orbit. Because I got to the different points in the orbit by multiplying the current set of points by generators. So I can also easily keep track of that. So I know therefore the orbit of 1 and the different elements of the group G which will map 1 to the different points in the orbit, and that gives me all the coset representatives of G sub 1 inside G, and therefore I have T1 easily. But now I want to get the next layer. How do I get to the next, to the coset representatives of G sub 2 inside G sub 1? And that's where Schreier's lemma helps me. So what it says is, suppose G is generated by A and H is a subgroup of G of finite index, so it's a general lemma. And R is a set of right coset representatives. Then all you need to do is to collect all elements of the form R1A, R2 inverse, which belong to H. So these Ri's are from the coset representatives. R is a set of all coset representatives. Collect all elements of the form R1A, R2 inverse, which belong to H. and I claim that's going to generate H. So now I know how to apply it here. It's very easy. I already have T1 with me. I have the generating set for G with me. That's the input. I can apply Schreier's lemma to get the generating set of the group G sub 1. And then I can continue. I will look for the orbit of the point 2 inside the subgroup G sub 1 to get all the coset representatives T2. It will give me the second layer in my strong generating set. Any questions? Okay. I should speed up. Okay, so let's do a quick proof of this. It's a nice little proof. So G is H into R because G is the disjoint union of right cosets of H and R is the coset representatives. And I also have RA is contained in BR. By the way, what is the cardinality of the set B? It's at, what is the cardinality? What is the bound on the cardinality? How many choices of R1 do I have? Cardinality R, many choices. How many choices of A do I have? Cardinality A, many choices. How many choices of R2 do I have? Sorry? Cardinality R. Okay, that's a possibility, but do I really have so many choices? If at all, so this is the same thing as saying R1A belongs to HR2. So clearly if R1A is going to belong to, it's going to belong to a unique right coset. So there is exactly one choice for R2. So cardinality B is bounded by cardinality A times cardinality R. Okay. So notice therefore by the same reasoning I just gave you that RA is contained in BR because that's the way it's defined. And now if I multiply by the generating set of G on the right, I have RAA which is contained in BRA and I know RA is contained in BR. So I can do this and therefore if I repeat multiplying on the right by A, I have R times the group generated by A is contained in the group generated by B times R. And since this is the whole of G, this is the whole of G, G is BR. But the group generated by B is sitting inside H. And this is a disjoint union, so you have no choice. B has to be the whole of H. That's a proof. Okay, so we are going to apply Schreier's lemma. But now there is a difficulty. As I just told you, my generating set is going to grow in cardinality. I apply Schreier's lemma to find generating set for G1, its cardinality becomes n times cardinality A. The next time it's going to become n square times cardinality A. By the time I come halfway down my tower of pointwise stabilizers, it becomes n to the power n by 2. That's not acceptable. What do I do? There's a nice reduced step that we can do. It's a nice little algorithmic step. Given an arbitrary generator set for G, I can efficiently find a generator set of size simply n square from it. And the proof is very easy. So proof is an algorithmic proof. So I've written the program for it. So all I'm going to do is, so think of the elements G1 to Gk as organized in a table. At the bottommost layer, let's put all the elements, all my generators which move the point 1 to somewhere. In my next layer will be all elements of my generating set which fix the point 1 and move the point 2 to somewhere, and so on. Okay? So let's organize the entire generating set like that. So bottommost layer contains elements which move the point 1. Now if two elements x and y move the point 1 to the same destination, which will happen if the number of elements in the bottommost layer is more than n minus 1, then I simply replace the pair xy with x comma yx inverse. It doesn't change the group. Yx inverse doesn't move the point 1, so it moves up the table to the next level. I repeat this, the bottommost layer, as many times as I need to. The cardinality of the bottommost layer will shrink to n minus 1. And this way I keep moving, sifting up elements in this table, and clearly every row contains at most n elements, and therefore the entire table will finally contain only n square elements, in fact strictly less than n square elements. And we haven't changed the group by doing the sift operation. Okay, so that tells us that I can efficiently transform anything into an order n square size generating set. Nice proof. Here is a more challenging exercise. Not only can I find a generating set of size n square, every subgroup of Sn I can transform into a generating set of size at most n minus 1. That's also a theorem, that every subgroup of Sn has a generating set of size n minus 1. It's not obvious, but it's true. And here is a hint for the exercise. You have to do some graph theory here. You have to do some combinatorics for this. Let ig be the smallest point that is moved by the group element g. It's a notation. And I draw the following graph. S is my generating set. I take the vertex set as 1 to n and edge set of all such pairs, ig comma the image of ig under g. Undirected graph. And I want you to figure out that as long as this graph has cycles, I can do a modified sift-like operation where I replaced xy by x and yx inverse, something a little more general, which will get rid of the cycles. So in the end, I will have a bunch of generators S such that the graph xs does not have any cycles. How many edges can a graph have which does not have any cycles on n vertices? At most n minus 1. And that's the reason why you can do it. A stronger theorem is true. Every subgroup of Sn has a generating set of size at most n by 2. But it's a very unfortunate proof. It's long and it relies on the classification of finite simple groups. And as far as I know, there's no efficient algorithm for finding. So if I start with an arbitrary generating set, I know there is one of this size. But can I find one of this size efficiently? I can find it brute force by looking at all subsets of size n by 2. But efficiently, I don't know. But it exists. Okay, so now putting everything that I told together, we are on the verge of our first algorithm. It's called the Schreier-Sims algorithm because it relies on Schreier's lemma, and Sims used it. So given an arbitrary subgroup by a generating set, you can compute a strong generating set, which is the union of these right coset representatives. Every element can be uniquely expressed as a product. You can test membership in polynomial time. And you can even compute the cardinality of the group in polynomial time. How do you do that? What's the cardinality of the group? It's a product of the cardinalities of the TIs, as I just told you. You can also uniformly sample from the group G given a strong generating set. Simply pick at random one element of T1, one element of T2, etc., and multiply them. That will be a uniformly sampled element of the group G. Okay. Assuming you can throw a die that has n sides to it for different values of n. Otherwise, you will get an approximate sampling algorithm from the group G, which is also a very useful thing. Okay, so let's do a quick running time analysis. The reduce step, you can check, it requires at most cardinality S times n many replacements. And in Schreier's lemma, computing an orbit takes at most so many steps. I'm assuming cardinality S is at most n square because I'll start with a reduce. And every time I descend the tower of stabilizers by applying Schreier's lemma, cardinality s grows to n cube, but I'll beat it down to n square by using this. And that costs n to the power 4 operations. And a quick estimate is n to the 6 plus this. But there are far more efficient algorithms for this. This is the basic algorithm, and the implemented algorithms in the GAP package, for example, group applications package, is very efficient. Okay. It's n times polylog and cardinality of G. So for small groups, it can be nearly linear time. Okay. Now I move on to a different topic. I want to recall the orbit counting lemma. Before that, remember that a fixed point of G is a point that's not moved by G. Fix of G is the number of fixed points. Orb of G is the number of orbits. And this is the orbit counting lemma. The orbit counting lemma simply tells you that if G is a subgroup of Sn, the number of orbits is the average of the number of fixed points. So it's useful to think in probability terms and write it as the expected value of the number of fixed points. Here is a quick proof for it. It's a double counting argument. You label the rows by the group elements and the columns by 1 to n. It's a 0, 1 matrix. You put 1 if I is a fixed point of G in the Gith entry. So, how many ones does the Gth row have? Fix of G many ones. How many rows, how many ones does the ith column have? How many rows does the ith column have? Is the number of elements of G that fixes the point I, which is basically cardinality of G sub I. Right. I also need to use Lagrange's theorem. The size of the orbit is cardinality of G divided by cardinality of G sub I. And so here I have the sum of cardinality G sub i's, and cardinality G sub I is cardinality G divided by cardinality of the orbit. And if I group all the terms appropriately, I will get the number of orbits on this side. I will move, so summation 1 by cardinality of the orbits over different points is just the number of orbits. That's because for all the points on the same orbit, you get the same 1 by cardinality orbit of I. That will add up to 1. And that will account for 1 orbit. So it will count just the number of orbits, and I can bring cardinality G into the denominator. So simple rearranging of terms. Okay. That's a proof. And now I come to the sales pitch, Jordan's theorem. Jordan's theorem simply says that if a subgroup of Sn is transitive, then the group G has elements that are fixed point free, elements that move every point of the domain. So G has so we are going to simply use the orbit counting lemma to prove this. So G has a single orbit. So this is 1 for G. And what is fix of the identity element? That's n. So fix of G is n when G is the identity element. So since the expected value is 1 and at least one number is more than 1, I'm assuming n is at least 2 in Jordan's theorem. Otherwise it's meaningless. Since the expected value is 1 and one number is more than 1, there must be one of the fixed G's which is 0, clearly. That's all that it says. But now, suppose I am given G, which is a subgroup of Sn by a bunch of generators, and suppose it's transitive. I know how to check that it's transitive because I can find orbits in polynomial time. I can efficiently check if G is transitive. But now I want to know whether G has a fixed point. I know G has a fixed point free element by Jordan's theorem. I just want to find one. How do I do it? Luckily, there is a theorem which says that, which strengthens Jordan's theorem in a very easy way. It says that there are many fixed point free elements in a transitive subgroup of Sn. At least 1 by n fraction of the elements of G are fixed point free. And the proof is very easy again. I'll do it in 2 lines. So let's say A is a set of fixed point free elements of the group G. Now, I have a transitive group, so number of orbits was 1. I moved the denominator in my orbit counting lemma up there. So cardinality G is the sum of the fixed points. I break it up into 2 parts. The sum of the fixed points when G belongs to G sub 1 and those which are outside G sub 1. And now let's calculate. Here, all these guys are going to fix 1. So that contributes a cardinality G sub 1. Let's pull that out. And here, the reason why this is at least this much is that the number of orbits, so if I apply the orbit counting lemma to G1, I know cardinality of G1 is, I know cardinality G by cardinality G1 is n. So cardinality G by n is actually, oh, okay, 1 second. So, sorry. Okay, let's see. Okay, let me pause this for a moment. So this is, so I get cardinality G is at least cardinality G by n plus cardinality G sub 1, and this part is simply at least G minus A union G1, because these are the fixed point free elements. All these are going to fix at least 1 point. So this is going to contribute at least cardinality G minus A union G1. So now rearranging terms, cardinality A is at least cardinality G by n. I'm missing this argument. I don't want to get stuck on that. So you can easily figure this out. Okay. So this simply tells you that the number of fixed point free elements is at least 1 by n fraction of fixed point free elements in a transitive subgroup of Sn. So that immediately gives me a randomized algorithm. If G is a subgroup of Sn given by a generating set, I know that I can efficiently compute a strong generating set, and I told you that once you have a strong generating set, you can sample uniformly from the group G by picking a random coset representative from each layer. And now the element that you get, you multiply all the coset representatives and that will give you a random element of G. The probability that it will not be fixed point free is 1 minus 1 by n. Say you run the sampler n squared times, the probability that you don't find a fixed point free element is e to the minus n. So you'll almost surely find one. But now I want a deterministic algorithm for it. So I'm rewriting the orbit counting lemma slightly differently. Let's say mu of G is n minus fix of G. So the orbit counting lemma says that the expected number of points that is moved by G is the average of the expected number of points that is moved by every element of G, which is n minus the number of orbits of G. All I've done is I've replaced in my orbit counting lemma fix of G by n minus mu of G. Now, for G transitive, because there's only one orbit, the expected value of move G is n minus 1. Now G sub 1 has at least 2 orbits. So the expected value when I take the expectation in G sub 1 is at most n minus 2. And G is a disjoint union of right cosets of G sub 1. Therefore, I can think of the expected value of mu of G, I can break it into 2 parts. It's the expectation over the coset representatives and the expectation over the cosets. And at least one of which is at most n minus 2. So I know that there is some coset for which the expected value is more than n minus 1. So if I can find this coset where the expected value is more than n minus 1, and I somehow try to repeatedly find subcosets of it, in the end I will find a single permutation which moves all the elements. Okay. This is called the method of conditional probabilities, which I'm going to use here. But now the question is, how do I compute this? I don't have the orbit counting lemma anymore to compute this, because this is a coset and it's not a permutation group. So I can't write down 1 by cardinality G summation number of fixed points. Okay. So now, we want to compute this expectation. In my matrix, remember that this entry is 1 if and only if G pi maps fixes the point I. Now the number of 1s in the ith column is the number of, so I want to count the total number of points. So remember that I want to count the total number of points that are moved here. Now, the number of 1s in the ith column is the number of elements of G sub 1 such that G pi fixes I. And this number is 0 if I and I to the pi inverse are in different G1 orbits, and is actually the pointwise stabilizer of 1 and I otherwise. So this cardinality is either 0 or this quantity. And it's something that I can compute because I can find whether these two things are in the same orbit of G sub 1 or not. Therefore, we can find all column sums efficiently. And since we can find all column sums, we can compute this expected value efficiently. So this is the method of conditional probabilities. I know here that there is a fixed point free element, and the expected value of mu of G is n minus 1. I come down to a subcoset where the expected value is at least n minus 1, and I can continue this process all the way. In the end, I will get a single permutation which will have more than n minus 1 fixed point, which will move more than n minus 1 points, which means it will move all n points. Okay. So at the dth level of this tree, we'll actually be holding a coset of the subgroup of G which fixes 1 to D, which maximizes this. So which is strictly more than n minus 1. Okay. Sorry, that was a bit hand-waved. So this method of conditional probabilities is something that has been applied in various combinatorial settings. The probabilistic method tells you that a certain object exists with high probability, and you want to deterministically find that object, and this is often useful in that setting. Okay. So here's one more point that I want to make. If G is not a transitive group, checking whether G has a fixed point free element or not is a hard computational problem. It's NP complete. So there are no known efficient algorithms for it. Here is an interesting theorem which kind of strengthens Jordan's theorem. What it says is that every transitive subgroup of Sn has a fixed point free element of prime power order. It's not an easy theorem because it relies on the classification of finite simple groups. It's a long paper. I don't know if there is an efficient algorithm for finding such an element. Here is a related, not quite related, but kind of interesting question which is vaguely related. This is the analog of Cauchy's theorem. It says, you know that if P divides order of G, there is an element of order P in G. Suppose G is given by a bunch of generators. Can I find this element? And using classification of finite simple groups, a deterministic algorithm is known for finding such an element. But this gives you a randomized algorithm for it. It pushes the classification theorem into the result, and the algorithm, you can have a randomized algorithm for it. The theorem says that if P divides the order of G, then there are many elements whose order is divisible by P. So we can get a randomized algorithm for it, because find a strong generating set and then sample with probability at least 1 by n, you will find an element whose order is divisible by P, and so you can find an element of order P by taking an appropriate power of it. Okay. Now I move on to a slightly different topic. Another computationally useful thing, which is very useful, for example, in the group applications package, where small base permutation groups can be dealt with differently, and the package deals with it differently. So suppose G is a subgroup of Sn, a subset of points is called a base if the pointwise stabilizer of that subset is identity. Okay. So if G is given by an arbitrary generating set, how easy is it to find a small base for G, the optimal, a minimum cardinality base for G? So this is a kind of generalization of bases for vector spaces, and as I told you, it's useful algorithmically. It turns out that finding minimum cardinality bases of permutation groups is NP hard. This is shown in 92. And that's true even for cyclic groups and groups with bounded orbit size. Okay. So there's no hope for finding minimum cardinality bases in arbitrary permutation groups efficiently. But you can approximate minimum cardinality bases. So here is something I thought is interesting, which we can discuss. So let's start with observing that suppose G has minimum base size of B, then G can't be a very large group, right? Because by the time I fix B points in my base, G becomes trivial. And I know that every time I fix a point, my group shrinks by at most a factor of n. So the size of G should be bounded by n to the power B. The minimum base size is B. An irredundant base is such that I start fixing the points alpha 1 to alpha d in sequence. I first fix alpha 1, my group shrinks. I then fix alpha 2, my group shrinks. The base alpha 1 to alpha d, it's a base because by the time I fix all the points, the group shrinks to identity. And every time I fix a point, the group must shrink by a factor. Then it's an irredundant base. Otherwise, I can drop some of the points in this list. So because it's an irredundant base, my group is shrinking by a factor of 2 every time. Cardinality of G is at least 2 power d, where d is the size of the irredundant base. So clearly, comparing the upper bound on G and the lower bound on in terms of irredundant bases, I know that every irredundant base is of size at most the minimum base size multiplied by log of n. So cardinality G is at least 2 power d, where d is the size of any irredundant base, it's at most n power b, and therefore d is at most b times log n. Finding an irredundant base is easy because I simply greedily fix one point after the other. So long as that point actually shrinks the size of the group, I can use the stuff that we have already discussed using Schreier's lemma to figure out when the group shrinks or not. And I can find an irredundant base easily. So I can get a log n factor approximation to the minimum base. But here is a better approximation algorithm. So suppose I've already picked alpha 1 to alpha I into my base, approximate minimum base that I'm computing. The next point that alpha I plus 1 that I'll pick will be from the largest orbit of the pointwise stabilizer subgroup of alpha 1 to alpha I. Okay? So I won't pick a point from any non-trivial orbit. That's enough to shrink my group. But I'll pick one from the largest orbit. If I do that, then it turns out that this yields a base of size log n times the minimum base size. And here is a simple argument for it. So if H is a subgroup of G, then G has an orbit of size at least cardinality H to the 1 power cardinality B. That's because by the time I fix B points, I am shrinking down to identity. So there must be, and I know that at every level I have these transversals which correspond to my orbits. So there must be an orbit whose size is cardinality H to the power 1 by B, because in B steps I am shrinking down to identity. So since H has an orbit of this size, I can take any one point of that orbit, and if I fix it, I will shrink my subgroup to cardinality H to the power 1 minus 1 by B. Sorry. Because the orbit is of size cardinality H to the 1 by B, so this will shrink to 1 minus 1 by B. That's an error there. So by picking greedily from the largest orbit, if I do that, if I pick B log n points, then every time I shrink by, in the exponent, a 1 minus 1 by B factor comes into the exponent. So by the time I pick B log n many elements, I get, and G is replacing G by at most n to the B, this becomes e to the B. So my group shrinks to size e to the B when I greedily pick from the largest orbit every time. And once I get to a group of size e to the B, I can pick any irredundant base that has at most order B many elements. So that gives me my claimed approximation factor of log n, which improves on the previous log n. Okay. Fine. So what happens when we are looking at other finite groups? So let's move away from permutation groups for the moment. So suppose G is a subgroup of the matrix group over the finite field FQ. The problem is that even membership testing is likely to be hard. And that's because even over 1 by 1 matrices, checking whether B belongs to the cyclic group generated by A, if P is a large prime, it's basically the discrete log problem, which is considered computationally a hard problem. So there is no hope for even solving membership testing for 1 by 1 matrices efficiently. And we can't treat these as permutation groups because we can't efficiently embed or even at all embed the multiplicative group over FQ inside Sn if, for example, Q minus 1 has large prime factors. So that's, in some sense, makes these groups very different from permutation groups. Maybe I can tell you a little more. Or I'll stop at this point and take questions, because I rushed through. So here is a bunch of references from which you can pursue this topic further.
Yeah, so open for questions.
Break for lunch?
I think your talk was crystal clear, or so people need some more time to think about it.
What you have told these many things, is there any application for the, means in real life situation for that? Because the algorithm and group theory you have mug up this thing, so is there any application for that in real life situation?
I don't know. And it's not important for me. It's simply the pursuit of algorithms for various kinds of discrete mathematical objects. That is the purpose here. Yeah, I mean, it can and does have applications, but somehow that's not the theme of the talk.
I think some of the applications may be pointed to in the references by Babai. In case,
well, probably even there.
You can chain through and eventually find the applications. Yeah. Any other question or comment? No? Okay, so let's thank Arvind for this talk.